All right, let's go ahead and start the lecture then. Today's going to be a little bit short. It's not a very long lecture or anything else. But let's kind of talk about what we discussed last time. We had a big, long covering of the history of how physics got broken and how we thought we understood a bunch of things, and then we looked a little bit too closely, and it turns out everything was significantly more complicated than we ever thought it would be. But there's kind of a history to all of that stuff, and there was a lot of really, really neat discoveries, and actually how a lot of that got started with some of the early issues was because of our study of electromagnetism, and we started talking about the four fundamental forces just a little bit. I said the weak force, the strong force, those are primarily inside of atoms. That's the only spot they're really relevant. But we might remember from a while ago that I've brought this up before, that things like the normal force and friction and all these other things, they're not real forces, I guess. It's not that they're not real per se, but what we attribute them to is not quite accurate. All of those forces, aside from gravity, so all the stuff that we saw in 191 besides gravity, are actually results of the electromagnetic force, right? That's actually the force responsible for the, object-to-object interactions. It's the atoms pushing against each other with the electromagnetic force. And we're not going to consider it on quite the scale like that, right? We're not going to redefine the normal force or anything. Our classical mechanics are safe. But it does give a little bit of insight, and we are starting to look into these details and peeling back the curtain a little bit. There's another curtain behind that one, but you get a little bit more each time. So the first thing that I'd like to discuss is really how we describe the electric force. And this is just a review from last time, but basically we said, okay, well, it looks a lot like gravity. Like a lot like gravity. You've got a constant, quantity 1, quantity 2 over r squared. The quantities this time are what's a little bit different. The quantity we use, instead of kilograms, we use coulombs here. But coulombs, the charge of an object can be positive or negative. And that's a really big difference, because mass is always attractive, but it's also always positive. There's no such thing as a negative mass, but for charge, we can be negative. And that means the direction of our force actually depends on the sign of the charges. So rather than deal with this inside of an equation, we've instead opted to talk about it in terms of pictures and just drawing our picture and looking at what should be happening. So last time I gave you guys this definition for the magnitude of the force between two charges, which was k, q1, q2. Both of those are in absolute values over r squared. And then what we would do is we would say, okay, are the charges like? Is it positive, positive, negative, negative? If it is, then they are repulsive towards each other. The forces will be pushing away. But if they're opposite charges, so positive and negative, then they're going to be attractive instead. And that's something that we essentially just have to find on our picture, right? There's not anywhere in the equation that tells us whether it's attractive or repulsive. And last time I discussed that there is a way to write that out, but honestly, we don't spend enough time on force to really bother with the more complicated equations. Because today, we're talking about electric fields. And this is going to be a little bit of a new concept. A field is kind of like a vector. In fact, we often call it a vector field. But it's not quite just in one spot anymore. A force is acting on an object at that particular spot, and it's not like the force is in space. It's a force happening to that thing right there. A field is kind of like a force waiting to happen. So for example, I could have a positive charge with a field around it, and it has a field surrounding it called the electric field. It's not exerting any force yet, but if I were to put another charge next to it somewhere, then it would start exerting a force. And the strength of that force goes along with the strength of the field. So maybe one of the easier ways to describe this is to come up with some sort of picture for this, right? So this is one of our PhET labs. This one's called the charges and fields. But if I take a positive charge, for example, all of these arrows represent what direction the electric field would be pointing at that point in space, right? And then the brightness talks about how strong that field is at any one point. So you might notice that it's everywhere, right? It's not just in the middle. It's not just in some space around it, but the field surrounds the entire particle, all the way from essentially the surface of the particle all the way out to infinity. There's an electric field there because of a charge. Right now, you're in an electric field, right? Whether you want to be or not. You can't get away from it because it permeates through all of space, even if it does get weaker and weaker and weaker towards the edges. So this might be a little bit difficult to kind of chew on. You might start by considering things like Earth's gravitational field or a magnetic field from a magnet, right? Consider things like that, where the magnetic field, especially, a fantastic example is the magnetic field of Earth. Because the magnetic field of Earth is always there, right? But the particles that it deflects aren't necessarily always there. You know, there's always some solar wind coming in and everything else, but that solar wind and all of those charged particles that it carries, they get deflected by the magnetic field, and the magnetic field exerts a force on those particles. Just as we will see, the electric field will exert a force on other charged objects. So you might initially think, hey, this sounds a lot like force, but you're just asking me to find more things in more spaces rather than just at one point. And kind of, but not really. We're going to end up preferring to work with electric fields. Well, at least I hope you do, because they can be a lot more useful than forces are. And this is why we're kind of allowing ourselves to use clunky notation for forces, because it's easy to explain, it's kind of easy to use, you can do it with a picture and then not have to worry about the vector math and everything else. But the electric fields are a much more elegant way to talk about a lot of these things. They're a much more useful way that you can describe collections of charges rather than just two charges interacting with each other. It's going to be an incredibly useful tool for us. And it's not just that a field is an abstract concept either. Fields are real things, right? They have physical quantities. Light is a result. Light is a traveling electric field. Specifically, it's a little bit of a wobble in the electric field, and that's what light actually is. So it's not like these things are not existing. A proton does have an electric field surrounding it. It's not visible like a particle is. And it also is, spread out everywhere. So it's a little bit different. We'll have to get into that bit by bit. But kind of a fun thing about this is that we never really stopped to think about gravity back in 191. How does an object know that the force from gravity is changing? How does it know to translate that force in the first place? What actually communicates to a mass that another mass is pulling on it? And it's the field. The field is responsible for transmitting that information, right? Both in gravity and in electromagnetism, the field is what's responsible for telling us about what the strength of the force is and also how that force might be changing. So I've got another example kind of pulled up here. If we look at this one instead, and I've paused it, so let's go ahead and reset this whole thing. But you can see if I've got a positive charge, these are my field lines as they extend out. Now, if my charge was to move somewhere, you can see the field changes with it, and it sends out, in essence, a signal, right? It sends information that, hey, I'm changing. This wave as we travel out tells us about that change of the particle and such a change in the force. So, this might be useful in case we have multiple charges. It's still useful for point charges, but it's really useful for a lot of charges, is what we'll find it most often for. But let's imagine that we have a collection of charges, or some source that's producing an electric field. Maybe it's a bunch of charges, maybe it's just one, maybe it's a big sheet of charge, something of that sort. We're going to find the electric field at that point by putting what we call a probe charge, right? So something that we're measuring. We're taking this probe charge, we're setting it down, and we're measuring the force exerted on that particle. We can define the electric field as the force exerted on that particle divided by the magnitude of the charge. And we get units that are not really that special. They're newtons per coulomb. So you plug in coulombs, charge, and you get newtons back out, right? That's all that we're really doing with these things. But what that means is that if we already know what the electric field looks like, we can rearrange this thing. And we can calculate the force at any point because we know what the electric field looks like. And the electric field is much easier to talk about. The electric field is much more general than any force because a force depends on that probe charge. But the electric field depends only on the source. So, let's try this in a problem, right? And one thing I want to keep in mind before we dive into that problem all the way, keep in mind both of these equations right here are telling us not only that the magnitude scales as force over Q, but the direction depends on force over Q as well. And there are no absolute value signs around this Q on the bottom. That's an important point. So, let's try this as a problem. Let's imagine that I have a 1 gram plastic ball, and I've charged it up with negative 3 nanocoulombs of charge. There's an electric field somewhere. I don't know what it looks like, but I know that there's an electric field. And while gravity is trying to pull the sphere down to the ground, the electric force is pushing it back up so that it's sitting in equilibrium, floating in the air. First, I want you to find what is the direction of this field. Draw out a free body diagram. Use that force, think about the sign of the charge to figure out what's the direction of the electric field. And then once you have that, find the magnitude of the field required to actually keep this thing up in the air. So I'm going to talk through essentially 2 different ways that I might do this problem. And one of them is very fast and sloppy, and one of them is much more mathematically rigorous. And realistically, I'm probably going to recommend that you follow along with the rigorous method for now, until you've got a really good sense of how the problem should go and why you're expecting certain values certain ways. And the reason I bring that up is because the mathematically rigorous way, it's going to be a little bit, naturally, it's going to be a little bit more tedious, right? You're drawing out more things, you're writing more equations, all that good stuff. But it mathematically leads you to the correct answer, and you don't have to do any crazy things like changing positives and negatives, or whoops, I grabbed the wrong angle, let me change to this angle instead. Right? If anybody has seen some of my office hours when I'm rapidly going through a problem, that's usually a fast and sloppy method, right? To get me to the correct answer, but it doesn't always make absolute sense, right? There's always some weird things that I do and then some corrections I put in afterwards. But until we get there, let's talk about what this thing is actually going to look like, right? So I said start with a free body diagram, because really that's going to help a lot here. So I know I'm on the surface of Earth. I'm expecting a gravitational force pulling me down just like that. And I'm expecting an electric force pushing me up like that. So what I could say, and I'm going to start this with the rigorous method. Proper math. I have the net force vector, and I know that the net force on this thing should be 0, and I know that the forces acting on it are the electric force and the gravitational force. So keep in mind again that vectors have positive and negative values kind of tucked away inside of them. So I know that f of g is pointing down, but that's tucked away inside of the vector. So when I do that then, I need to look, okay, well, f of e, that's because of an electric field, right? So that equation is described as q times e, okay? And I've got a good sense that that's pointing in some direction in the y direction, right? And then I can do a similar thing with gravity, and I can say, okay, well, F of G, the magnitude is mg. The direction is negative j hat. It's pointing down in the y direction. And I should put little arrows on top of these, shouldn't I? Because these are vectors, and that's how we say that these are vectors. Okay, so once I've done that, I can say, okay, well, here's a negative j hat, and I'm looking to try and find E, so let me sort this whole thing out real quick. Right? What I can do is I can rearrange this equation and say, okay, we'll add this side. So I'm going to have mg j hat is equal to q times E. Better yet, mg over q j hat is equal to E. Now, you might immediately look at this and say, haha, so the electric field is pointing in the positive j hat direction. Not quite. We're almost there, but we need to plug in the numbers as our final step. And when we plug in the numbers, what we find, and I do the quick conversions here, so 1 gram turns into 0.001 kilograms. G, still our good old 9.8. Our charge is negative 3 nanocoulombs. And j hat, just kind of sitting there. So what we find is that our electric field is actually going to be, and I'm pulling up my number here so I'm making sure that I'm accurate, negative 3.267, yeah, negative 3.267 times 10 to the 6th j hat newtons per coulomb. Now, that's not the magnitude. Keep that in mind. The magnitude, if I was to write it out, I should probably spell magnitude correctly first, but the magnitude, remember, is just going to be, in this case, positive 3.267 times 10 to the 6th. Magnitude doesn't care about positive or negative. It doesn't care if I have components in all three directions, right? You do Pythagorean's theorem to find the length. And here, it's only in one direction, so I don't need to go through that steps, right? Because 3.267 times 10 to the 6th squared, square root of that is just 3.267 times 10 to the 6th again. So our magnitude should be a positive 3.267 times 10 to the 6th. Now, that entire way did not require me to look at what's going on with my picture, right? I kind of just jumped straight to B, or newtons per coulomb. Yes, for this final part. The Canvas answer is in kilonewtons per coulomb. Keep that in mind. So, that's the proper math way to do it, right? I am treating all of my vectors with proper care. I'm being very careful. I'm making sure that everything's in vector notation. I'm adding up all the vectors, and then the negatives that are tucked inside of the vectors, they kind of come out once I start plugging in for those things, right? This is like a surefire way. You don't have to worry about the picture. You don't have to worry about, I don't know if it's positive or negative or what I'm expected to see here or anything else, right? You follow the math, and it spits out an answer at the end. That's cool, but sometimes I'm kind of lazy and I want to just get done with the problem really quick. So if I would have looked at this thing like I had maybe in 191, let's do this in, we'll do this in this red color. Here's the sloppy method. I say f of y, well that is going to be f of e minus mg. And then I can say, okay, well, this is QE is equal to mg. And then I can say E must be equal to mg divided by q. And now here's the problem. I might have done this in 191 and totally gotten away with it. But the difference here is that Q can be a negative value. And if Q can be a negative value, this entire time I'm kind of just throwing this around like it's going to be positive. But if it's not, what does it mean to have E as a magnitude be negative? Well, it would be impossible if it was just a magnitude. So when I'm doing it like this, it's not quite a magnitude, it's still kind of like a vector. I've just tossed away all of my vector notation, right? And that's why this is kind of a sloppy method. It's a little bit faster because I don't have to bother, writing j hat every single time and what's positive j hat, what's negative j hat, all of that stuff. I can just jump into this straight away. But I think this is chance for error is really what this comes down to. Because in a case like this, I would find a negative E, but I would have to know what E looked like before I started the problem, or this answer might not make sense. Here, I know that E points down, and let's do that in red. I know E points down because I just found it in the last problem, right? But also, if f of E is going up, and I'll write this out. If f of E is greater than 0, or rather it's going in the positive y direction, and Q is less than 0, then this equation right here tells me that E is in the negative y direction. And there's a few different ways that I can use to talk about this, and I will later. Once we have a better grasp on fields, this is a little bit easier to describe. There's, again, kind of a network of ways, a big web of different descriptions that we can use, that we can, any of our weaker pieces, we can reinforce with the surrounding ideas. But this is what I mean by a sloppy method. It will certainly get you to the magnitude without much trouble. But getting the direction correct is maybe a little bit more up to chance than it should be. The proper math method with vector notation used properly is typically going to be your safest route, even if it does take a little bit longer. So right now, while we're getting started by talking about fields and all of this kind of stuff, I'm going to recommend taking... I'm trying my hardest. While we're getting started with this stuff, though, I'm going to recommend you go through and be rigorous with it. Use I hat, J hat, K hat if we ever need it. Go through all of these extra steps for now. And as you get better at these, as you practice through more of them and start to understand the problems a little bit better, it'll become more obvious what shortcuts you can take and what it means when you take those shortcuts, right? I have been doing this long enough that I can go through the sloppy method very quickly, and if I see a negative sign somewhere I don't expect there to be one, I can be like, oh, well, I know it's not supposed to be there. I know that the math should work out in such a way that that would cancel, something like that, right? Go through the proper method for now. So, let's imagine I've got 2 point charges. We know what the force looks like between those 2 charges, right? K, Q1, Q2 over R squared. What if we follow this method that we just used to describe what the electric field should look like? Well, then it stands to reason that the electric field from a point charge is just dividing by Q2, right? If I have my Q1 in green, and then Q2 is my probe charge at the point P, well then divide by Q2, and all I'm left with is K Q1 over R squared. And that's the electric field. Now, this one is, I think, a little bit more useful as well, because you'll notice that we don't have an absolute value sign around this equation, right? What we're really doing here is we're saying, okay, well, just take this thing right now take into account that the charge is positive, take into account that the charge is negative. That tells us what direction the electric field is going to go. See, we've got two different options here, because if my charge is positive, then I'm going to see an electric field like the orange arrow right here, right, pointing away. It's going to continue going radially from my charge to my point and then keep going a little bit from that, right? That's the direction the force would be pointing. If the charge was opposite instead, and it was an attractive force, then my force would be following along the blue arrow instead. But since there's no charge there, it's just the field. So the field would be pointed along the blue line. Now, it's a little bit strange seeing this r hat. That was not something that we included in force. And for now, there's a few different ways that we can try and consider it, right? The first might be, okay, well, it's just following along what direction the force would be. But you'll notice that the force could have been two directions. So at the very least, we've got it isolated down to an axis, but maybe not anything in particular quite yet. We'll come back to that in just a minute. But it's sufficient to say that you could recreate the force equation, right? If you just focus on the absolute value instead, like we had with force, and determine the direction afterwards, that's a doable thing as well. You just take the absolute value of the charge and you get the absolute value of the field. And that works great. If you just like to draw this on a picture, you can absolutely take that method just as well. But we should talk about how we actually draw these things out, right? Because drawing these pictures is going to be extremely important. If you're not drawing pictures for these things already, you really should. So there's two different schools of thought in drawing the pictures, and sometimes I use one or the other. I'm not really picky with which one. It kind of depends on how fancy I feel that day. The method on the left is essentially saying, okay, if you're drawing at a vector field, then you're going to make a bunch of different points, and you're going to draw the direction, and then the length of the vector tells you about the strength. So if we are looking at a point charge, we know it goes over 1 over r squared. So it gets smaller and smaller as you get farther away from the point, right? And that's exactly what we see on the left here. The closest points have the longest arrows. As we get farther and farther away, they get shorter. But they're always pointing radially outward. And let me come back to that thought in just a little bit. If we see the negative charge instead, we notice that, okay, if I just flip the directions on everything, right? So now instead of pointing outwards, we're pointing inwards. The other way that we can do this, and probably what's going to be a little bit more common for you guys and what I'll often default to, is a really, really fast method to just draw some arrows real quick. And then basically what you get is that the closer the lines are, the more intense the field is at that point. So there's a high density right around it, right? All the lines are pretty close together. As we get more spaced out between them at the edges, it's a weaker field. And that's a really fast and easy method to use, right? Sometimes I'll kind of go in an in-between of these two things. One last thing that I do want to kind of mention here, this central point, that these are 2D slices of a 3D field. All that you really need to remember is that reality is in 3 dimensions, right? 3 spatial dimensions at least. And when we're in 3 dimensions like that, don't expect that the charge is ever just going to exert a field in a circle. It's emitting it as a sphere, right? So keep that in mind. So I kind of brought up this r hat is messy, to say the least, right? It's a little bit confusing, and if you're going to get confused at any spot in this lecture, I'm going to guess that this is probably going to be the place. So, r hat is essentially a radial unit vector. So first, remember what a unit vector means, right? Just like I hat, j hat, k hat, it's got a length of 1 and no units, so it never does anything to the magnitude of the vector, but it does tell you about the direction. And that's a really important distinction, right? All it's really doing is telling us where does this vector point. The magnitude is covered by everything else. R hat is only going to tell us the direction. But it's radially away from our point charge. So basically, if we start from our point charge and we want to find what is the electric field at some point P away. One way that I can find this just using a picture is to start from my point charge, to draw a straight line out to my point, and then go a little bit farther and draw an arrow. And that's what r hat should look like. Right? And it's a really, really, really useful tool because you might notice that there's all of these different r hats surrounding me. I've got maybe r hat 1, r hat 2, r hat 3, and they all tell me different spots along this thing. One way that you can actually define this, not that we're going to talk about this immediately yet, but one of the ways that you can find this, if you know what the r vector looks like and divide it by the magnitude of r, you get r hat, which is just the definition of a unit vector. But we won't talk about it in too much detail yet. If you haven't already seen that one, don't worry about it. We'll talk about that again later. So now, what do we actually do with this r hat? Well, it tells us essentially how the components of the vector are going to be broken up. And that's really where this thing starts to shine. R hat can be described as cosine of theta times I hat plus sine of theta times j hat. Now, this is always in terms of the unit circle, right? So I'm always going to start from my positive x and wrap around to my point. And if I plug in that theta every single time, it will land me at the proper breakdown for my r hat. So that's always what I'm going to recommend for this one. Right? That is probably the easiest way to handle this at any point. Start from the positive x-axis, wrap the angle around until you get to wherever you're going, right? So in a case like this, it's really nice and easy, just up a little bit, right? But if we're going to one of these other ones, we might see something like that instead. But if we just do something like that, then we can plug it in directly to cosine of theta times I hat plus sine of theta times j hat and be done with it and have our answer immediately, right? And this will break down. You might notice as the cosine of theta is the x component, which, yes, we've seen that before. Sine of theta is the y component. We have seen that before, right? Right over here. That's kind of exactly what that's doing. And then, as always, we can always get back to our unit vector, cosine squared plus sine squared. Take the square root of that. That should get us back to 1. Right? So, I want you guys to try it. Let's say I have a positive 12 nanocoulomb charge located right at the origin, so right at 0, 0. I want you to draw the electric field of this particle. And I've got 3 points in particular that I'm really interested in. And when you're drawing this picture, I'd ask that you try and be careful about the lengths of your arrows as well. Right? I want you to just consider that point while you're doing this one. So if the fields are supposed to be equivalent or roughly equivalent, make the arrows about the same length. If one field is supposed to be stronger than at another point, make the stronger one a little bit longer. Just to help you visualize where the strength of that field actually is. And then once you've done that, find the electric field vector and component form at point B, or if you'd like to do more of them, I'm always welcome to it. I'll solve out for all 3 if you'd like, but I'd ask you to at least do part B. Here's my positive charge, right? I keep using red for positive, so let's just go with that one. So before anything else, if I think about what should my electric field from this point charge look like? E is equal to K, Q over R squared, and then this R hat is an important point, right? And I've kind of made mention now that R hat is kind of like a radial unit vector. So what that would tell us is that, okay, Q is positive, R is always going to be positive, R hat is always going to be pointing away from my point charge. So my electric field, again, I'm kind of ignoring what length these arrows should be for now. I'm just giving a general sense of direction, but I would expect something like this, right? And if we go back to our little simulation here, that is what we see. With a positive charge, if I had a positive charge, say right here at the origin, and let's ignore the arrow that's directly under it. But I can see that along the x-axis, I'm pointing directly away. Along the y-axis, I'm pointing directly away. And up here, kind of in where we expect to see our -5, 5 and -5, -5, we get a sense of what kind of direction we should expect right off the bat. Right? And so if nothing else, that tells us a lot about what we should see in terms of positives and negatives. before we ever have to solve out any of these magnitudes, we kind of know what direction everything should be going. So let's go back to our problem here, and let's talk about the 3 points we're looking at. So I've got one right here. Call this point A. Got one right here. Call this point B. One right here. Call this point C. Right? And what clever names those are, because those are how I define the points. So, I kind of said this before, but the easiest way, if I want to find r hat on the picture, the easiest way to do that is to start from the charge, draw a line out to the point, right? So it looks kind of extra thick in this case, right where it is. I know it's a little bit hard to see on this one, but that's okay. R hat is if I took that line and I made it a little bit longer. Like that. There's r hat, and I'll call that r hat of A. And then I can do this same thing. I go to point B, so I draw my line all the way out to point B. R hat. Points like that, call that r hat B. And I'm just specifying these points. These are all different possibilities for r hat. I could pick a 1 point way out here in the top right corner. I could pick an r hat anywhere, and they're all equally fine because the electric field is not a one single point. It is a vector field. And that means that it is in all space, we expect to see some sort of quantity. We are just looking at the strength of the field at these particular spots. So, sorry, gotta get my windows sorted out here. So my last thing, I drew my line, I extended out just a little bit to find r of C. R hat of C. Okay. So those are my 3 r hat values, right? Now, there's a couple different things that I might consider. What I'm thinking of right now is I might as well figure out some angles while I'm at it, right? Because remember that we talked about r hat. For any r hat, we can always say cosine of theta I hat plus sine of theta j hat. And as long as we started from the positive x-axis, that was totally fine. So, A to 0, right? Nice and easy. I expect B to be at an angle, start from the x-axis, go all the way around. This will be 135 degrees, and I'm finding this one geometrically, right? It's an not an equilateral triangle, but the 5 centimeters, 5 centimeters, right? That's 45. So that was 135, and then I could go the extra 90 to wrap around all the other way, or if you want to go as a negative 135 for this one, that works just as well, right? That's completely equivalent. It'll work just fine. So what that means then is that I can split these 3 up if I would like. But I might as well just kind of do these in order. So let's do these, if you're only doing one at a time, let's do this. I know that my charge is positive this entire time, so I'm expecting my electric field to go alongside in this case. And I'm just finding these on the picture first. Whoops, let me make that a little bit more. I'm not a very accurate artist. Here's the electric field at point B. Here's the electric field at point C. We've got those 3 points. Okay, so let's start from A. Before we find E of A, it's better to find R of A. So let's back up for a minute and let's say, okay, let's find this thing first because we're going to need to plug it in anyways. And let me do that in purple so we can distinguish it a little bit better. R hat of A, I plug in 0 degrees. I plug in 0 degrees, cosine of 0 is 1, sine of 0 is 0. So r hat of A is just I hat. And if we look at our picture, yeah, it points in the x direction. We see that. That works. Then we can move on to E of A. And I'm going to call that distance R of A, right? Just to keep everything kind of nice and consistent. I know that R of A is 5 centimeters, so this is going to become K, Q, and I'm just going to leave it's the 12 nanocoulombs for all of these, right? Times I hat. We plug all of this stuff in. at the very end, we should find something like 43,150 in the I-hat direction, newtons per coulomb. So there's our first answer. For part B, the one that we're actually interested in answering for Canvas, well, this is going to be a little bit more messy. I've got 135 degrees, so what I'm actually going to get now is a split. It's not going to be the full I-hat. It's not going to be the full J-hat. It's going to be somewhere in between both of them. My calculator would tell me, or I can know if I have my unit circle memorized, that this is negative root 2 over 2 I-hat plus root 2 over 2 J-hat. So then, E of B right, same thing as before. I start with the exact same piece. Now I'm going to plug in some of these details. Down here is a little trick that I've got. If I know that R of B is equal to the square root of 0.05 squared plus 0.05 squared, then squaring R of B gets rid of the square root, right? And I'm just left with 0.05 squared plus 0.05 squared. And then finally, this nasty bit. And what we end up with then, I should probably close that parenthesis, shouldn't I? Is negative 15,260. I've done a little bit of rounding here. You might have a slightly different number, but 15,200 something, right? So negative 15,260 I-hat plus 15,260 J-hat. That's what I've got for this one. Answer number 2. Finally, we'll go through one more, R of C. And we might immediately notice that this is almost exactly the same. It's now a negative 135 degrees, which just means that the y has flipped. So it's still a negative root 2 over 2 I-hat, but now it's also a negative root 2 over 2 J-hat. And I'm not going to go through all these steps a second time, right? I already just did this, but sans a minus sign. So E of C, I can immediately just kind of say, okay, you know, I know where this is going. E of C, negative 15,260 I-hat minus 15,260 J-hat. And this is a little bit more of a rigorous method than just kind of throwing some things out there. Now, that being said, you could also do this finding magnitude first, right? You are also more than welcome to treat this thing like a picture, to think about, okay, well, I know that the magnitude is going to be pointing in this direction. Now I can split up the components if I just figure out what one of these angles is, right? I just need to make a triangle out of these things and find the angle from that. Find the two components based on that. You could go the route to say the magnitude of the electric field is equal to K Q over R squared and find the direction later. But it's good practice with R-hat to do the method on the right for now. That's what I recommend. R-hat is going to be very, very useful. It is not just useful for this one particular case. It's going to continue to be useful, and we're going to continue to see it in a lot of different ways. So that's what I'm going to recommend to use more often. With that, it's a little bit of a short lecture this time around, but that's all right. I think, but on that note, we'll end the 22-2 lecture.